We're from CoreLogic. My name is Ross Ganguly. I run the enterprise architecture practice for CoreLogic. And with me is Ashish, who is running the geospatial architecture for CoreLogic. We're here to talk about how our journey began with the property insights. This is where we have started working with Carter. Year and a half ago, we partnered up and we wanted to talk about some of the lessons learned and what we did with Carter and the plans for the future. Before we begin, like Hologic is not a consumer company that everybody can connect to. I wanted to share like who we are and what we do and what our experience with geospatial prior to working with Carter. So as we know, like Hologic is an ecosystem. We are primarily a data solution provider for a lot of various industries across real estate, mortgage, and tax servicing companies. So we work with like various market segments like real estate, mortgage, insurance, even with government and housing agencies. With that experience, we have a lot of interactions with the various personas. Like if you think of a property, because we primarily are a property-centric company, so we work with all the residential properties across United States and also Australia and UK. And we have a lot of experience around like working with lenders, contractors, buyers. And what we learned over time is geospatial data is very critical to serve all these industries. Because if you think of a property, the first thing is where is it located? It's the geolocation. But then you start going on the chain of providing value for the customer. There is a lot of data that we have, but unless you have the connectedness within the data, they cannot really accelerate and help the customers at the end. So you have the discrete data point, but then we try to start connecting. So a few years ago, we started thinking how can we connect the data and how can we really bake in the geospatial across all our data assets. And we came up with this whole 360 view that we started building a few years ago. We partnered up with Google. We are using Google a lot on our data journey. And as we build it up, one thing we started learning that it's hard to identify a property. If you think of a property, you think of an address, but property is more than just address. Like there is a parcel boundary, and as you get more into it, it's really complex property graph that you have to create where geospatial comes in. And unless you have the unique identifier of the property, you really cannot connect the property with the various industry data segments like insurance, if you think of claims, if you think of other tax related information, that is really challenging. So with Property 360, we started to start with the location, then we layered up the imagery, the structure, the neighborhood information, so on and so forth. And we started building our whole ecosystem. Now that was all great. We had a lot of geospatial expertise within the company. We have like 157 million parcels in the United States that pretty much covering the entire United States. We have 170 million plus structures which are within the parcels. A lot of the natural hazard data that is used by the insurance industry to rate file and also do other damage calculations and whatnot. But then as we started to get to the next level, which is about climate risk. So that is taking all the data that we have and trying to apply what is the climate risk scenarios across your properties and start aggregating those at the various admin level boundaries like the census blocks, the states and whatnot. This is where we started finding a lot of challenge because when you start calculating that much of data, you think of the volume of data that our model is generating. We have about 2 billion records in BigQuery. We have 200 million plus geometries that we have to visualize in a web application. And this is where we started working with Carto, and thanks to Carto's team, we got a lot of support from Carto. So really thank Javier, Alberto, and others because we had endless hours of conversation. We have Anthony here as well, who works intimately with this project. So he also helped us a lot. So this is where we started to see that yes, it's good to visualize data if you have a few attributes, but now when you start having lots of attributes, you have to use more techniques to really render it and have it at a scalable way. If you go to the next. So we want to talk about this. Just to give a little bit of what these climate scenarios are, just a quick preview, and then we'll really dive into what's the lessons learned.
Yeah, just before I dive into that, like one of the basic questions that we are trying to solve is that we want to tell you what the climate risk is to your property. And what's going to happen in like 10 years, 20 years, 30 years, and how it affects you. And a lot of times when we think about the climate scenario, the climate usually is often talked about in terms of different scenarios. So like you will hear in the media like, oh, there's a 1.5 degree C scenario, there's a 2 degree C scenario, and so on. And so one of the big reasons why this is done is that because our future is not determined. Like it depends on what we do today. And so as a worldwide, like one of the things that IPCC, which is the primary agency behind designing these climate scenarios, is doing is understanding what will happen if various governments actually fully cooperate. What happens if we take certain compromises on economic output. And so based on all of this, they try to understand the various factors that kind of goes in, and that renders into multiple different scenarios. And this is kind of becomes our input into our scenario and projecting that back to the property. So one of the ways in which the climate scenarios are actually described is what is called RCP. It stands for Representative Concentration Pathway. It's a bit of a mouthful. But really what it really means is that if you think about the planet, like the amount of energy that's coming from the sun, that's a net input. And then Earth basically radiates back some of that is reflected back. So if your temperatures remain more or less constant, they need to be in balance. But if you increase the amount of greenhouse gases in the atmosphere, then some of that is retained. And that retention is described in terms of these RCP parameters. And effectively what it's saying is that the RCP 2.6 is saying that if we as a world take all the mitigation, really put a step forward and make that as our big priority, the amount of heating that the atmosphere will take will be roughly equivalent to getting 2.6 watts of energy from the sun per square meter. And in that scenario, your temperature rise will be limited between 1.5 C to 2 C. So this is the scenario, this is the case where this is almost considered like the best case scenario where we're all working towards mitigating climate change. Now, the three scenarios that I'm describing are the one we use in our simulation, but effectively they are, most people kind of refer to them as low, medium, high. What is the impact of climate change? The lowest amount is if we do high level of mitigation, that's RCP 2.6. 4.5 is we do some, but again, the world isn't perfect, so that's where we may end up lying up. And 8.5 is basically when, let's say, it's business as usual, we don't do anything. And that's kind of what it leads to, is like 5C scenario. And just for reference, like the Paris Climate Agreement, that's described as RCP 1.9, which was an aspiration goal that, let's say, can we keep it below 1.5? And so usually when we are simulating, these are the kind of the three ones we are really looking into.
So then when you look at the climate, and we are in the business, right? So one thing is the science part, but in the business, what you're really looking into is not only the physical and the financial risk. That's why we have so much data that we have to visualize this around, like, what is the physical risk to the structure? So if you think of the porcelain linear of structure, we need to analyze and simulate each structure to understand the physical risk. And then we layer in the financial risk, which is around what are the losses? Because if you think of the insurance industry, we need to tell them, okay, if the climate changes in a certain way, here is the impact to your business portfolio. And that's what we are trying to visualize in the maps, so that the amount of data is not only about how many property and structure you have, we have to layer in the number of climate scenarios, and then we have to simulate for multiple years to understand what will be the time series impact on the property or in the neighborhood. And that's how the reason we're talking about all this is the challenge that we ran into about the volume of data that we had to visualize through the map. Because everybody loves map, everybody wants to move around in the map, but there's a lot more data and complexity that are baked into, and that challenges that we ran while we are doing.
Yeah, and before I dive, I think I want to just give a quick demo of the application. So just kind of,
Just to showcase what we ended up. So this is the application that we have, and we'll talk more about how we made it more performant. But this is the nationwide climate risk scenario, and like Javier, you were talking about, there are filters on one side, there's a map on the other side. That's how people love to see things, and then they want to use the sliders on the left to visualize the map. Our challenge was like as we were going through this initially, it was not very performant. Now we were talking about how we work with Cardo and slowly evolved and improved this performance to the level we have.
Yeah, and just talk about the application. So one of the things that everybody's asking the question is like, okay, we understand climate change is happening, we understand temperature is going to rise, but oftentimes people relate to that by in terms of like what it does to the various natural disasters, what it does to the wildfire, what it does to my coastal flooding. So one of the things that we were trying to show through our application is that let's bring it down to each property level. Let's show you the climate impact of various perils on each of those structures. So in this application, just to kind of give a little idea, this is showing an aggregation based on zip code. So this is a RCP 2.6 scenario. And let's say if I just kind of zoom in, let's just go to Manhattan. And then at this point, like we're taking that knowledge on our wildfire models, applying the changes that comes from the climate scenarios, the changes in precipitation, the temperature, and based on that, we basically now projecting it down to every individual property. So now in this, we can kind of zoom on any of these properties. So you can kind of see like, even though they are kind of in the same block, the actual amount of damage may be different. Maybe their foundation is different. Maybe their the construction cost, the construction material is different. So these are the kind of things that we start looking into to just kind of give you a better sense of what it may actually mean. Now, what kind of showing here is that this is a composite risk, so which is what we call as like kind of like a net average of various different perils like wildfire, flooding, both coastal as well as inland and so on. And what we're really showing you is like if you sort it by the single family residential home, and even within a block, you kind of see some variations in the climate risk. And let's put some, yeah. So this is also like a different, same thing, but a different view. In the first view, we were looking at the actual net impact from a physical perspective. This is more of a financial view. So if the certain properties are underinsured, then we can actually kind of tell you that these might have a greater impact on those. And so this is one of the reasons why for us this project was like we really had to aggregate a whole lot of data to kind of get to this level. So now that you've kind of seen a little bit of the application, I just want to kind of talk about what data do we have to really aggregate. So we talked a little bit about the climate scenarios, the RCP 2.6, the 4.5, and 8.5. So that's kind of like our basic scenario planning in terms of low, medium, and high kind of impact. And then what we really want to show is that what is the effect of this climate scenario for all the 13 perils. And in addition, also kind of show you what is the financial impact in addition to that, not only the physical as well as the financial side. And then we also wanted to show this on all the 4 time horizons. So 2020 is kind of like our baseline. This is where we are starting. And in our actual models, we went all the way to 2100, but this is, in our application, we kind of limited that to these 4 time scales. And we wanted to do this for all the 140 million structures. So these are all the structures for the properties, all the properties that we have in the United States. In this one particular example, it's just color-coded based on the wildfire risk. This is actually from Boulder, where on the left side, you're kind of seeing the open space where usually a lot of the wildfires will originate and it can travel inward into the city. While individual properties were great, we also wanted to show aggregated risk. And so we also took all of this data. We also took 8 different admin boundaries from all the way from the state counties to individual census tract and blocks. And we performed aggregation to kind of bring some more analytics for our customers to understand. We also did some aggregation on H3. Another thing that we wanted to do was like also break down the concept of a property. So property isn't just one thing, not everything is the same. So we wanted to make, a lot of our customers are mortgages, so big banks with mortgages. And so they really want to understand what is the difference of the impact to the portfolio for single family homes versus multifamily. And similarly, we have other customers who are trying to understand the same impact of what is the impact of drought have on my agricultural land. So not only all the parameters that we currently have, we also divided in based on the property types. And then we also did aggregation for each individual property types for zip codes and other admin areas. So when we started looking into all the data, we just have a lot of attribution. And that was kind of our first realization. If you look at the number of scenarios, which is 3, number of time horizons 4, perils, the economic parameters we're looking at, if you multiply all of them, we're well over 2,000 attributes that we're looking for. So that's kind of where our initial challenge. So when we first started, let's say, our first goal was, well, why don't we create one tile set per geometry? Because that sort of makes sense. Like we have one structure layer, we have about 9 different aggregation layers, including H3, and let's say can we pack all these attributes in it? And when we started packing them, we try to reduce all the attributes as much as we can, but really it's a lot of attributes. Even on a structure, it's 390 attributes when you include all the combinations of climate scenarios, the different perils. And when it comes to aggregation, it's even worse because the aggregation changes based on the kind of the property type. So you take that value, multiply with 6, now you suddenly over 2,300. So the first thing is like vector tiles, you can only pack so much before you start losing before you need to start dropping features. So one thing we consider is that can we increase the vector tile size, like go from 1 megabyte, 2 or 3 or so on. But then you're paying a performance degradation. Like the client has to now download more data, the tiles are slower to load, and it doesn't always look great. And initially we tried to make one of these aggregation tiles with a lot more attributes. You see the problems right away. Your feature's gonna drop, and especially when you're showing a map of like all the zip code boundaries and suddenly you see a lot of gaps, it doesn't look great for our customers. They really want to see the entire view of the zip code, and maybe your data isn't there. So that was one of the first key things. Like we knew this was too much data, and we were right. We were able to prove that. So next attempt, we said, why don't we reduce the number of attributes per tile set? So let's just generate more tile set. It's not ideal, but let's try that. So what we did is we again go back to our application, and the way our customers want to really visualize climate data is by each peril or by each property type. So for example, for structure, we have 13 perils, and after just like some experiments, we just come to like 30 attributes more or less kind of looks reasonable. It's a reasonable amount of performance that we can kind of go with. So that means that for structures, we had 13 tiles. And for aggregation, we end up having 78 tiles because we also had to do based on each property type. So again, total 91 tiles. It's a fair number of tiles that we now have to generate for all of these scenarios. It's a lot, but at least now we can proceed. And so that was our first step. So how do we do this? Well, this is kind of like our data pipeline. Most of our data is in BigQuery. Like we said, like roughly 2 terabytes of data, 2 billion rows, and so on. We are pretty familiar with Tippecanoe. This is kind of our bread and butter tool that we always use. So what we first started is like, all right, we're going to extract the data from BigQuery. We'll containerize Tippecanoe. We're going to scale it up and generate those vector tiles. And then we're going to push it over to some renderer, like whether it's any cloud-based like Mapbox, or do a local tile server, visualize, and use that as a feedback loop. If there's some problems in the data, well, we go back, we go fix it, and rinse and repeat that cycle. But that was not very efficient, and we soon realized like we just have a pretty slow ETL process. And there's no problem with the individual tool. It's just like we're spending a lot of time extracting the data, especially when you have this amount of data, it takes time. And every time you're basically going through the cycle, making some updates, making another extract, it's just slow. And another big problem was like our iterations were just kind of slow, like in terms of getting feedback from clients or even for internal teams. So we extract the data, we basically generate the MB tiles, but then pushing that out to any cloud-based like solution, Mapbox or so on, we've been wasting a lot of time. So that was our first realization that we can't really come back to a very good solution for our clients. And yep.
Yeah, and that's where we started looking into like how can we keep the data the way it is, not do the ETL, because that's obviously slows you down. Our data keeps changing quite a bit. And we started working with the Carto technologies and the BigQuery. So we started figuring out how we can leverage Carto to solve the same problem here.
Yeah, so this was like our attempt too, and definitely, thanks Ricardo for helping us on this project. So we wanted to keep everything the same, but just let's leverage Carto's BigQuery toolbox, given that one of the big advantage for us was that we all for data is in BigQuery. That's kind of where we do most of our processing. So it was a very natural fit for us to use Carto. So we saw some immediate benefit from just even not optimizing the number of tile set. The first big advantage was that we can just skip the extract. We don't have to extract from BigQuery to some disk and run a separate process, because the analytic toolbox have all these functions from Carto that we can actually use for creating the tiles. So again, it was a big part of the step we just skipped right away. And second, like, we again don't have to, as a team, we didn't have to spend a whole lot of time building our own pipelines, scaling those individual containers, and managing that process, because BigQuery can do that for us. So again, like for us, again, from a team management perspective, that was again a huge win, because instead of teams spending the time and building these DevOps pipelines and dealing with all of those things, they can really focus on the real work. And that was a huge win. And the other thing that we really enjoyed was that the ability to do rapid prototyping. So using Carto, like we can run the SQLs, we can actually visualize the data, we can visualize the tiles, and that allows us to actually really improve the velocity. So all of our data stays in BigQuery, we create those tiles, we go to the Carto builder, we can now run some SQL queries, and we can actually right away visualize. So again, for us, it was like huge gain in our team velocity.
Yeah, I think we changed the game, like, because now that we can iterate so fast because of the Carto Builder. If the business is looking for the visualization of the tiles, we can do it with Carto Builder. You don't have to move the data. It stays within BigQuery. Using the Carto Builder, we can do the rapid prototyping before we actually take it to the production. So that also helped us a lot in our journey.
Yeah, actually, the modeling team really enjoyed, because that allowed them to actually see and understand it even better. Because so far the process was kind of slow. It took time.
But so to interrupt for a short answer question, when you mention rapid prototyping, do you mean that?
Can you just repeat it?
But do you mean rapid prototyping means that you are using just Builder or creating those maps, or is just that you are using Builder and then integrated using the fetch map functionality that you have?
To build maps.
Yeah.
So we have our own GIS teams, right? So they are also using the Carto Builder to rapidly prototype. We also even prototype, I think, for the CRA to understand how it works before we get. And that's what helps is like the instant feedback from our business users. Like they look at the map, they can give us feedback before we spend too much time doing the development, taking to the production. This is a much faster route to develop maps before, and helped a lot.
Excellent.
Yeah. You guys did a great job.
Yeah, so I think this really, like, the point for us was like it really solved a lot of the problems for us. Like two bottlenecks for us was like extracting the data and also visualizing the data. They were a real bottleneck, and I think this helped us solve a lot of the big core bottlenecks.
But we wanted to do more because that was not enough, because the speed we were getting is still not optimal for a web application. Like there was still some slowness, and that's where we work more to see how we can optimize it further. And
Yeah, so the next attempt was like, we don't like 78 tiles, or 91 tiles rather, that's way too many. Ideally, we wanted to go back to the idea like, you have one geometry type, let's create one tile, can we kind of get back to it somehow? So that was kind of our next attempt in how we can just kind of start optimizing this. So one of the first thing we kind of thought about is like most of our boundary data is fairly static. The state counties, the zip codes, they don't change that often. And even for the structured data that we have, it does change, but again, it's reasonably static data that we don't have to keep doing the same thing, same work over and over. Now, the main thing that's changing between all of these boundaries is just all of our attribution, climate attribution for different scenarios and so on. So our main goal, like the first thing that we really wanted to do was like, can we separate these two as a two separate entity? We manage them as a separate life cycle and dynamically join them. And this is kind of where using DeckGL to just kind of dynamically join the data really came in very handy. So to join the data, again, there's different strategies that we use for something like the aggregation. Like if you look at like states, counties, zip codes, there's a limited number of those. There's only like, say, 30 to 40,000 zip codes. There's only 3,000 counties. We did some pre-processing, and we sent down the data that was just usable for rendering and changing the colors down as a single protobuf. And so this allowed us to kind of optimize all the aggregated layer, all the data aggregation. And then we just joined this data on fly by just overloading some of the DeckGL functions for rendering the tiles. Now, we use protobuf, but we don't really think that that's necessarily what everybody has to use. There's some great examples on DeckGL documentation on how you can pass binary data, just pass directly to the GPU. So there's plenty of examples. I think there's some future talks on the GeoParquet as well. But I think the key thing is that if you're sending down a lot of data, try compressing it, try sending down as a binary data as much as you can. Now this worked for our the aggregation tile because the data was still limited. When it came to structure, that was still not enough. Because we have 140 million structures, it's still a fair amount of data that we need to process. So we needed a second strategy. And so what we really did was like, our strategy was like, if the data is too big, let's tile it. Let's split it up just like we split the geometry layer into Z, X, Y, and let's join this data on the DeckGL layer. And so in this example, what we really ended up doing is like we took our base geometry tiles, the structure, the admin boundaries, we associated like an ID with them that we can use for joining, and we created those geometry tiles that can be fetched from the DeckGL. Then the second thing we did was like we took all the data attribution along with that ID, and we mapped them to the X and Y for the zoom for the various zoom levels. So in other words, we're basically creating an identical BigQuery table, ZXY, with a data field, and the data is a protobuf which contains all of our attribution data. And then on the DeckGL layer, DeckGL is great for flexibility. It allows us to overload the tile and load functions as well as change on the viewport. So every time it is fetching the geometry tiles, the ZXY, we actually just go and make another call to fetch the ZXY for our data tile. And then we can dynamically join them. And that allowed us to really be very flexible for fetching the data. Now we can have like a true separation between the data tiles as well as geometry tiles, which allowed us to like really be independent. Like now at this point, not only our climate risk data, if you want to visualize some of the other kind of data, we can do it very easily just by generating those data tiles and reusing our geometry tiles over and over.
So one thing we do recommend, like if you have really small attribution, like you have a 10, 50 attribute, you really don't need to do this level of complexity because there is a cost to maintain the separation and the cost of processing the data. But if you have a lot of attribution, I think this is a much preferred way to do it.
So another thing, kind of needless to say, you really got to optimize your caching. Now, once we separate the geometry and data tile, we just realized that they have a different life cycle. Geometry tiles, they don't update that often, so we can use longer TTLs for our caching. And similarly for the data tile, the attributions do change. I mean, we are running models continuously, we are updating the data, so we can use a shorter TTL. So again, we can really optimize how we're using our cache as optimize the cache for generation and reducing the number of tiles that we need to create. Now, in our example, we utilize the Carto CDN for both of these. So again, use caching as much as possible because it really allows you to save a lot of money. Again, thanks to Carto, we got excellent support. During this process, we also found lots of ways we can optimize, and we definitely worked with both Carto as well as Google to fix a lot of the ways in which we can actually improve our performance. Another thing that we utilize pretty heavily is that you don't have to create your vector tiles for every possible zoom level. It's just not necessary. You create it to a point where you have enough resolution. So like, for example, this is just kind of showing our structure data for Manhattan. We created the structure tiles for just zoom level 14 and 16, but the resolution was good enough that you could keep zooming on your DeckGL and it will still keep that on the map. And so then we really avoided creating way more tiles than necessary. So again, another tips that anyone can use. This is another thing that we considered but then ended up using is that right now we have about 8 different standard administrative area. Now, if your application's workflow is like for each zoom level, you have a very predefined way of visualizing. For example, like say zoom level 0 to 5, you want to see states. Say 6 to 8 or something, you want to see counties, and then maybe zip codes and so on. So if you have a very well predefined pattern, you don't need 7 or 8 different tiles for each admin boundaries. What you can actually do is like collapse them into a single tile. And on the analytics toolbox, the create tile set functions allows you to use these columns, a min max column, where you can actually define for each row where that particular row will need to be rendered. And so what you could use is that you can use some kind of an IDs, like composable IDs, like state counties. You can use FIPS code. A lot of the census tract is FIPS code plus addition of census tract ID or the block group ID and so on. So you can really create some composable IDs that is really easy for you to just generate and then be able to join them and display whatever data you want to do. So some of the lessons for us, one thing like I was talking about that we just realized very quickly, we spend a lot of time in ETL and not doing the real value. And so one of the takeaways for us that we just want to share with everyone is like just consider your true cost of your data pipeline. How much time are you really spending in extraction and just data movement, like from one stack to another stack to another stack? And if you can really compress that, that is a huge win. And it can lead to like huge productivity gain. And for us, like a cloud native approach made a perfect sense, given like how we are internally structured. So again, we don't think there's anything necessarily wrong with the individual tools that we previously used. It's just like when we put it all together, it just made sense for us. Again, separation of the geometry tiles from data tiles made a big impact because now we are really optimized for tile generation because we really don't have to keep recreating all these combinations of administrative boundaries plus all kinds of data. And for us, the climate data model is just one of the many projects. And if you consider properties, there's just all kinds of extra attribution that you have. So now we can really reuse some of the work we've already done to accelerate some of the other projects.
Yeah, and on this one, like what we see that not about our industry only, this can be applied for any industry. Like if you have a lot of large data sets that you are trying to visualize, separate the geometry versus the data tiles, depending on how frequently the things are changing. You definitely can take a lot more advantage of the caching because now you can do granular caching at the geometry tiles versus the data tiles. So this definitely adds a lot of value. Does need a little bit more thought around how you are processing the data because you have to split the geometry and the data as part of the data processing. But that is worth it. Like if you have a lot of large data sets, it's definitely a lot of benefit that you can get.
Actually, yeah.
You want to-
Actually, one thing I want to talk about is one of the other advantages of separating the geometry from the data tile is that once you fetch the fetch the geometry tile on your map, even if you switch to kind of get the different data and you want to show a different coloring, you're not refetching the geometries. And I can kind of really show this on the, so like if I'm here at this point, all the geometries are already prefetched. So if I say go from composite to flood, so you can kind of see the geometries are already there. I'm just fetching the data and then dynamically joining them. So again, it reduces your bandwidth cost and also like just the latency response.
Then we had to also do a lot of the optimization on the BigQuery side because we are using BigQuery as our primary data warehouse. Partition strategies, keep an eye on that because definitely you have to organize the data depending on the data warehouse. Like BigQuery is a columnar database, so we have to do the partition strategy based on the columnar database. We had the benefit of splitting it by Keras, but for like being like in general, try to find a way to do the ZXY based strategy because then you can align the tiles with the partition data, so it's much easier to programmatically do it. If you use a different partitioning strategy, you have to add some extra logic, but ZXY definitely helps on the partitioning. Same with the clustering because partitioning the table is one, but with the columnar database, if you can reorganize your rows in a certain way, then you can cluster the rows in the same nodes. Again, that helps you to get better performance out of it. So do keep those in mind because as you're looking at the mapping and visualization, how you organize the data is equally important. And similarly with the infrastructure, we ran into some quota issues because of our high volume, like it was 2 terabytes of data with significant amount. So keep in mind, sometimes you may not get the performance because you don't have the adequate quotas. So if you're using BigQuery and all, I don't know about Snowflake, maybe there's always some soft limits. So work with the vendors. If you see some performance challenges, that's another area.
Yeah, and this is something that we were pretty excited about H3 because from our perspective, the climate risk is not based on your zip code or your state boundary. It doesn't respect that. It doesn't really care about it. Because what we really wanted to show was like the uniform distribution of how the risk changes from one area to another. But as we were rolling out, and it doesn't necessarily resonate with all your clients. A lot of our clients are government entities, FEMA, and so on, and they are really responsible for their own administrative boundaries. And so they really wanted to understand the data from their perspective, what they're responsible for. So that's another something to keep in mind. H3 is great, but it may not resonate with all your clients. So you just kind of have to kind of feel it out with what really makes sense for them.
So next steps that we're looking into, because we got a lot of success with this climate risk data, we know how to address high volume of data and visualize. So what's next for us, what we're looking in terms of our geospatial domain that we have within our company, definitely the photorealistic 3D tiles, like we are very excited what Alberta showed us this morning, so we'll work closely with them to see how we can take it to the next level, because that is really resonating with a lot of our customers because it's easy to walk the neighborhood, it's easy to visualize the property you're about to buy. So there's a lot of exciting use cases around that. Same with, what we see, the other thing is if you think across the enterprise, not everybody is a geospatial expert. We love geospatial, we talk about geospatial all day, but if you're really working with the web application team or others, there's sometimes a lack of understanding. So we are trying to work internally within our company how to roll out timing as a framework so that we can start building a center of excellence. So the application teams doesn't need to know much about the web tiling or how to render geospatial data, but we can have a center of excellence that can build it for them. That will help them to get faster time to market. So that is really we're working internally to see how to do that. The other two are around like how to explore DeckGL for advanced visualization across multiple platforms is again something that is one that we are also looking into and more to come. Exploring with Carto on the geospatial analytics because we are an analytics company. We are trying to figure out how we can leverage the geospatial data to advance and improve our data richness. Again, areas that are very evolving and very new to all of us here. We don't have a lot of an answer how to do it, but this is something where we will be keep exploring more and start innovating more and looking forward to engaging in with Carter to kind of navigate this path as well. Overall, our experience with so far has been fantastic with a lot of the stuff that we have definitely gained over the course of last few months and quarters. Any questions?